So, in the last lecture, we have talked about subgroups, how we define subgroups, and then what are the conditions. So, we define order of a group, order of an element, then we presented few examples, then we defined the definition of a subgroup, and then we gave some tests to check whether a subset of a group is going to be a subgroup or not, and what are the ways to check it. So, there is one step subgroup test, and then there is two-step subgroup test, and then there is finite subgroup test. Okay, and now I'm going to talk about subgroup examples of subgroups, and the proofs of the next few theorems show how our subgroup test work. We first introduced an important notation which says that for an element A from a group, we let this denote the set which has elements like a power n, given that such that n is coming from integers, and in particular observe that the exponents of a include all negative integers as well as 0, and the positive integers a power 0 is defined to be the identity. Okay, so we present now the theorem. Says that and this is 3.4. This says that A is a subgroup is a subgroup is a subgroup. The statement says let G be a group and let A be any element of the then the set generated by A is a subgroup of G. And proof of this is that since A is contained in the set generated by A, so A is non-empty or not empty. Now let A power n comma A power m are in the state generated by A, then A power n, A power m minus 1 are equal to A power n minus m, which are in the set A because they are somehow the powers of A, and the set generated by A contains the powers of A. So by theorem 3.1, A is a subgroup of G, and that's the proof. Now, what kind of a subgroup which is generated by A is a subgroup which is generated by an element of a group A is called the cyclic subgroup of G. Generated by A. In the case that G is itself equal to subgroup uh, the set generated by A, we say that G is itself cyclic. G is cyclic, and A is its generator. The generator of G. A cyclic group may have many generators. So notice that although the list A minus square, A power minus 2, A power minus 1, A power 0, A power 1, and A square has infinitely many entries, the set A power n, is that n is coming from Z, might have only finitely many elements. So the more also note that since A power I, A power j is equal to A power I plus j, and it can also be written as A power j, A power I. So we can say that every cyclic group is abelian. Okay. Now let's give an example. And it is example 9. So in U of 10, 3 generates the set. It is 3, 9, 7, and 1. And it is itself U of 10. So then for 3 power 1 is 3. 3 square is 9. 3 cube is 27, which is under mod 10, 7. And 3 power 4 is 1. 3 power 5 is 3 power 4 into 3, which is 1. And then 3, which is 1 into 1 into 3, which is 3. Similarly, 3 power 6 is 3 power 4 into 3 power 2, which is 9, so on. So in this case, 3 power minus 1 is 7, since since 3 into 7 is 1, and 3 power minus 2 is 9, 3 power minus 3 is 3, 3 power minus 4 is 1 again. Now 3 power minus 5 is 3 power minus 4 into 3 power minus 1, which is 1 into 7. So 7, and 3 power 6 is 3 power minus 4 into 3 power minus 2, which is 1 into 9. So 9 and so on. Okay, so you can do negative powers and then positive powers also, right? Then next example is that in Z mod 10, two generates the set which is 2, 4, 6, 8, 0. Now remember, a power n means NA when the operation is addition. Okay, and then example 11 says that in Z, say generated by minus 1 is Z itself. Here each entry is the list. Here each entry is the list, like minus 2 into minus 1, comma minus 1 into minus 1 into minus 1, 0 into minus 1, comma 1 into minus 1, comma 2 into minus 1, and so on, represents a distinct group elements. Okay, now we say that the example 12, that in Dn, the dihedral group, dihedral group of order 2n, we let R denote the rotation, a rotation of 360 by n degrees. Then R power n is going to be R 360, which is E. R power n plus 1 is going to be R. R power n plus 2 is going to be R square, and so on. Similarly, R power minus 1 is R power n minus 1. R power minus 2 is R power n minus 2, and so on. So that R generates the set which has E R up to R power n minus 1. We'll see that then that the powers of R cycle back periodically with period n. The powers of R cycle back periodically with period n. Visually, raising R to successive positive powers is the same as moving counterclockwise around the circle one node at a time, whereas raising R to successive negative powers is same as moving around the circle clockwise one node at a time. So let's draw a circle by which we can depict this. This doesn't look like a circle to me. This one looks okay. So now let's have a point, a node here, a node here, and a node here, and a node here, and a node here, and we have dots, and we can say that if it moves counterclockwise, Then this is r power n, which is e. This is r minus 1, which is r power n minus 1. This is r power minus 2, which is r power n minus 2. This is r power n plus 2, which is r square. And this is r power n plus 1, which is r. Okay, this is what I said. If you move the counterclockwise around the circle, we raise r to the successive positive powers. If you move the clockwise, we raise r to the successive negative powers, and then that's it. Okay. Now, in chapter 4, we will show that order of the set generated by A is equal to the order of A, and that is the order of subgroup generated by A is the order of A itself. Okay. For now, say that for any element A of a group G, it is useful to think of A generated, say generated by A, is the smallest subgroup of G containing A. Okay, so let's write this point. For any element A of a group G, it is useful to think of, say generated by A, is the smallest subgroup of G containing A. And we can extend this notation to, so this notation can be extended to any collection S, any collection S of elements of G from a group G by defining the set generated by this collection is the subgroup of G containing the collection of elements containing collection of elements S, subgroup of G with the property with the property that this contains S, and if H is any subgroup of G containing the collection of elements S, then H also contains the subsets subgroup generated by these elements. Thus, this is the smallest subgroup of G that contains S. And the set is called the subgroup generated by the collection of elements S. And we illustrate this in the next example. So, example 13 says that in Z10, Z20 actually, Z20, we get 8, 14, the elements generated by 8 and 14, or the set generated by 8 and 14 is nothing but 0, 2, 4, up to 18. And this is also generated by 2. And Z, the elements, the subgroup generated by 8 and 13 is actually similar to Z. In D4, the subgroup generated by the elements H and V is actually equals to H square V and HV, which is nothing but also equal to R naught R 180 H and V. And in D4, the subgroup generated by R90 and V is nothing but contains R90 square, R90 cube, R90 power 4, then V, R90 V, R90 square V, R90 cube V. Okay, and this is also equal to D4 itself. In R real numbers, the group of real numbers under addition addition, the subgroup generated by 2 pi and under root 2 is actually equals to 2a plus b pi plus under root c under root 2. Given that ABC are from R, BC are from Z actually. Okay, and then in the set of complex numbers C under addition, the subgroup generated by 1 and iota is A plus B iota, given that A comma B are real or actually coming from integers, and this is known as this group is known as is called the Gaussian integers. Okay. Now we next consider one of the most important subgroups. Okay, and that is, we define it as a definition. We call it center of a group. The definition says the center denoted by Z of G of a group G is the subset of elements of G elements in G that commute with every element of G, and ensemble we write it Z of G contains elements from G such that X is XA for all X in G, and the notation Z of G comes from the German word for the center is Zentrum. So that's why we call it Z of G. And then we have a theorem which says that three point five that center is a subgroup. The statement is the center of a group G is a subgroup of G. And though it's long proof, but I want to present that proof. The proof says that for variety, we shall use the theorem 3.2 to prove this result. We can use 3.1, but we should use 3.2 now. So let's not write this and just write clearly. Clearly, E is in the center of G. So Z of G is non-empty. Now suppose A and B are center of G are in center of G, then AB into X is nothing but A into BX, which is A into XB by using the property of the center, and that is going to be A into XB, and then that is going to be XA into B, and that is going to be X for all X and G. And therefore, the product AB is in center of G. Okay. Now next, we assume that an element A is in the center of G. Then we have then we have that AX is equal to XA for all X in G. Now what we want is A inverse X is XA inverse. So what we want is A inverse X is XA inverse for all X in G. So informally, all we need to all we need to do obtain to obtain the second equation from the first one is simultaneously to bring the A's across the equal sign, and that is actually we want AX is XA, where here we go from here to here we go from here to here, and this becomes XA inverse is equals to A inverse X, right? But be careful here, groups need not to be commutative. The A on the left comes across is A inverse on the left, and the A on the right comes across as A inverse on the right. So formally, now we did informally, now we do formally. Formally, the desired equation can be obtained from the original one by multiplying it on the left and right by A inverse, like so. So we would get A inverse AX A inverse. This is A inverse X A inverse. And now this side, different side, we do A inverse A X A inverse, and this side we would do A inverse X A inverse, and this is going to be E X A inverse. This is going to be A inverse X E, and this is going to be X A inverse is A inverse X. This shows that this shows that A inverse lies inside the center whenever A is. And that's how we use the two-state subgroup test to prove that center is a subgroup. Okay, and now we show that we define another that although an element from a non-abelian group does not necessarily commute with every element of the group, there are always some elements with which it will commute. For example, every element A commutes with all the powers of A, and that's true. So this observation forms the next definition and theorem. But let's note this term which says that every element commute every element commute with all of its powers. Even though it is coming from non-abelian group. So next definition is that centralizer, what is the centralizer of, of A and G? Now, what is the centralizer? Let A be a fixed element, of a group G. The centralizer of A of A in G is denoted by C of A is the set of all elements in G that commute with A. Ensembles C of A can be written as the set contains G in G such that GA is AG. Now, how is this different from the center of the group? In the center of the group, you check that all the elements in this of the group commute with each other, right? So what do you check? What is the center? It contains elements from the group G and also elements from the group G, and does not fixes any element. It talks about which elements of the group commute with each other, and all those elements which are of the group which commutes with each other are in the center of the group. But here in the centralizer of an element, we are fixing an element and we are checking that which elements of the group are commuting with that element particularly. Okay, there's a difference. Now we present a example. So example 15, which says that in D4 we have the following centralizers. The C of centralizer of R0 is actually E4 itself, and the centralizer of R180. Okay. Similarly, the centralizer of R90 is equals to a set which is R0, R90, R180, and R270. And this is also equal to centralizer of R270. Remember the definition of the centralizer. Elements from the group which commute with the fixed element. Okay. Similarly, centralizer of H is going to be R0, H, R180, and V. And this is also equal to the centralizer of V. And centralizer of D is the set which has R0, T, R180, and D. This is also equal to centralizer of D prime. Okay. Notice that each of the centralizers in example 15 is actually a subgroup of D4. So the next theorem shows that this was not a coincidence. Okay. So the theorem says theorem is centralizer C of A is a subgroup. And we say in a statement that for each A in a group G, the centralizer of A is a subgroup of G. Okay, and the proof of this is similar to the 3.5. A few terms. For every element A of a group G, the center of G is a subset inside the centralizer. Also, observe that G is abelian if and only if the centralizer of A is actually equal to G for all A in G. Okay, and here we will end our lecture because we have exhausted the subgroup list a bit. There can be more. Thank you so much.